Good evening. My name is Johannes Henn. I'm a theoretical physicist working at the Max Planck Institute for Physics in Munich. So we're here to talk about the ERC project. So the ERC project, the Universe Plus, it's called Positive Geometry in Particle Physics and Cosmology. Our project is about finding a new language of mathematics that helps us to describe fundamental physics.
Yeah, so we're here in Leipzig, Germany, at the kickoff workshop for this project at the Max Planck Institute for Mathematics in the Sciences. So I'm one of the directors at this institute. So we have 4 principal investigators on this grant. So besides Johannes and myself, there's Nima Akani Hamed from the Institute for Advanced Studies in Princeton, who unfortunately cannot be with us tonight. But the 4th one is here, so Daniel Baumann is a leading cosmologist from the University of Amsterdam. And so we're here meeting for the whole week with a really exciting array of talks introducing the subject.
Yeah, maybe I can just add that. So I think it's a Universe Plus is like an adventure that brings together, 3 different subjects: particle physics, cosmology, and mathematics. Some of those subjects have relationships that are kind of go back quite some time. So, for example, cosmology and particle physics related in the early universe, but the relationship to mathematics is much more recent. And so,
yeah, and it's really going to go in both directions. I think mathematics will contribute to physics, to cosmology and particle physics, but we also will gain very, very much by learning from techniques and questions and ideas from the physicists. So I was told that this box contains interesting questions, and so we will take them one at a time and see what we can come up with. So the first question is, why do particle physics, cosmology, and mathematics go so well together? Maybe we'll start with you.
I can start. So I'm actually not entirely sure whether it's correct to say that they go well together, but it seems to be the case that some of the deepest questions about the nature of our universe seem to require a synergy between those subjects. And so that synergy between particle physics and mathematics and cosmology, in fact, naturally arises in the very early universe where the conditions were very extreme and required a combination of those 2 subjects. Relationship to mathematics is more recent, goes back to the discovery of positive geometries of just 10 years ago. And then the relationship between cosmology and mathematics really is only being developed, and it remains to be seen how close ties there exist there.
Yeah, of course, the relationship between physics and mathematics goes back a very, very long time. But I think historically it's been other areas of mathematics, differential equations, dynamical systems, function analysis, that have been closely connected to physics. And here the kind of mathematics that plays a role is algebra, discrete geometry, combinatorics, and that is very, very recent. How about particle physics? Why does it go well together with cosmology and mathematics?
I think maybe the question could have been, why is mathematics so effective at describing fundamental physics? And I think there's a very long tradition for that, going back to calculus, which was developed to describe the motion of the planets. And also more recently, if we think about Einstein's general theory of relativity. So I think there's a long tradition for interconnections between mathematics and fundamental physics. And here in this project, we're developing these connections further on a very specific topic. And we're rooted in new observations about geometrical aspects that are relevant, that we think are relevant to these areas.
In fact, we've seen this today. So today was the first workshop day, and we really witnessed some wonderful talks that emphasized precisely this role of geometry in the physical settings. Maybe I'll move to the second question I pulled out. So what is your personal motivation for the Universe Plus project? Maybe again, Daniel, would you like to start?
Yes. Well, I think one of my motivations is really to learn from kind of all these brilliant people that are already part of the project, especially young people that will come into this project and will come up with fresh new ideas that we haven't yet thought of. And so I'm very excited to kind of be part of this and learn, as much as I can and contribute to my own guidance to the next generation of researchers.
So why do you hang out with us, Johannes?
Yeah, I can totally echo this. I think it's just exciting to be able to work with and exchange ideas with brilliant people. And I think also the point about early career scientists is absolutely crucial. I mean, we can see it at the workshop here. There's so many people with fresh ideas. It's just, I feel a lot of energy working on this project.
Yeah, and it's really young people talking to each other and discussing who would not have otherwise come together. I think already officially the program, the project will only start in 4 months, but we're already seeing a lot of interaction, collaboration, and for me this is very, very gratifying. I mean, I'm the old man in this group, and I see myself really primarily in a mentoring role, and it's been very gratifying and exciting so far.
I think it's fair to say one can see already some enthusiasm in the community, just from the fact that this project is starting, as you just said, and people are eager to work and contribute to it.
Absolutely. Let's see what else is in the box. Maybe I'll start with you now, Johannes. Which hidden principles beyond quantum mechanics and space-time do you hope to reveal?
Well, this project has as a basis very new observations about geometric structures being relevant both to particle physics and to cosmology. And so I think it's exciting to develop these further. And one very important aspect of our project is the connection with mathematics. So I'm particularly interested in seeing what new questions one can ask from a mathematics viewpoint, but they then be relevant to developing physics further.
So our colleague Nima sometimes talks about beyond space-time. So I thought space-time is so established, right? So isn't it?
Well, there's kind of thought experiments that suggest that space-time, at the most fundamental level, at very short distances, is only an approximate notion. One way this thought experiment goes is that if you want to measure very short distances, you need to put a lot of energy in a small region of space. At some point, that region of space will collapse into a black hole. So there's a minimal distance that we call the Planck length. Beyond kind of space-time becomes a very fuzzy concept. And so that's a thought experiment. That thought experiment becomes much more dramatic in cosmology, where we do have the entire universe kind of originating from a small region of space. And so that space-time there manifestly emerges from this Big Bang singularity. And so both of these instances suggest that there should be a reformulating of the known laws of physics that doesn't put primacy in this concept of space-time, but replaces it with something else.
Yeah, and for me as a mathematician, it would be tremendously exciting to be part of this, as this new insights into physics, fundamental physics get developed, to witness it firsthand by myself and with my students.
Maybe just to add something to what Daniel said is that what this idea is that space-time is only an emergent concept. What this is telling us is that what it motivates us to do is to look for a different starting point, where then the traditional ways of thinking about physics are not the input, but rather the output.
Very good.
Would you
yes,
like me
please,
to
Johannes, take a turn.
See what else is in this.
Thank you.
So what do we have here? Well, maybe this one's for Daniel. Why is there a need for a new mathematical language to describe physical phenomena in cosmology?
Yeah, so I think some of the open questions in cosmology are related to the beginning of the universe, where the physical conditions were so extreme that they go beyond the known physical laws that we can probe in terrestrial experiments. And so we think of one option is to use mathematics as a guide to try to develop, theories that appear natural to the eyes of a mathematician, and then also try to deform those theories in ways that are natural to the eyes of a mathematician. And that those type of mathematical concepts we hope has physical consequences.
Yeah, one thing that I found striking about the difference between cosmology and particle physics is that in particle physics we have very serious experiments and experimentation, and many people are involved in carrying out experiments. Well, there are no experiments in cosmology, but still we have data.
Mm-hmm. Oh, yeah.
So this is also interesting for me as a mathematician, because at this institute there's a lot of talk about mathematics of data and data science. Maybe you can comment on that aspect.
Yes. Yeah, I was almost shocked for you to say that we have no experiments, because we have a lot of observations, of course, and I think that's the distinction you were making. So one big difference between cosmology and particle physics is that we can't reproduce the experiment of the Big Bang. It happened once. There were no observers, living at the beginning of the universe. We can only try to trace back the origins of our universe from.
How does that work?
Well, there's patterns that we see today, and we play detectives. We try to reconstruct the history of the universe from the patterns that we see today. And so it's observational. It's an observational science rather than an experimental science.
Bernd, you said that data plays an important role for you in mathematics. Could you say a bit more about that and how that's particularly relevant in this project?
Yeah, so in this group in particular, we're very interested in mathematical aspects of data science. So methods from statistics, probability, and optimization are being studied with algebraic tools. And what I'm hoping secretly is to bring something back. I mean, physicists in this field really have tremendous insight in evaluating integrals and doing sophisticated calculations. So I certainly like to bring something back to statistics and optimization. But I think ultimately, I believe we might be able also to contribute with our insights. So scattering amplitudes at the end of the day are probabilities, and relationships among different probabilities are at the heart of algebraic statistics. So that's one thought I have. Although this will not happen right in the beginning of collaboration, I think this will be a couple of years down the road.
And maybe I'll start with you. What significance does the promotion of early career scientists have in the overall project?
I think it's a very important aspect. I think we already saw this when we heard this when we discussed our motivation. So really, the training of postdoctoral fellows and graduate students is very important in all our groups, and will in particular be in this project. Diversity is very, very important. I think we believe in excellence through diversity, so diversity as a means of excellent science. And ultimately, we want to show a path for careers of young scientists. And it's been very interesting for me to learn that even between mathematics and physics, the career paths are quite different. That, of course, in physics, we have more research institutes, there's more facilities for doing fundamental research, and ultimately people maybe take positions there. In mathematics, it's often about teaching. So people spend a couple of years in a research postdoc type environment, but then staying in academia really means going to university and teach, and often teach very basic classes. And anyway, so to make a long story short, I think it's a wonderful opportunity to help young people to find their path.
Mm-hmm. I think this is also what's special about the grant, that it gives us the opportunity to provide kind of an environment for young people. And I think young people in my field are really the lifeblood of research. And so my research would be nothing without my PhD students and postdocs, and this grant really allows us, I think, to bring together some of the best people in the field under this umbrella of the ERC grant.
And they can spend time at more than one institution. So traditionally in most projects, one gets hired in one place and works on one project, but here, because we have the three different sites, Princeton, Amsterdam, Munich, and Leipzig, there's really an opportunity to benefit from more than one group. So I think that's going to be quite exciting.
I think it's really an opportunity for people who are doing their PhD, for looking for an exciting project, because they have precisely these different institutes to go to. They can profit from the workshops we're organizing. This is in fact one really important element of the project that we're starting now, to foster this exchange between the different fields, between people at the different institutions.
I mean, we will also have schools, so this we still need to discuss the details. So there will be schools aimed at the graduate student level. Ultimately, we're hoping also for outreach to possibly even at the high school level. And So this will be all part, but as I said, the official project is not starting until 4 months from now, and so the details of this will have to work out.
I think one plan is to have a high school textbook on positive geometry.
That would be great.
Okay, let me. Okay, I think this is for Bernd. What's the very positive about positive geometry?
Yeah, so first of all, positive really refers to positive real numbers. So really we are doing calculations, we're looking at objects in a real space. But positive domains of positivity are regions in space where some functions are positive. So at the most basic level, linear functions, if you have a collection of linear functions, the regions where those are positive are called polytopes or polyhedra. So these are shapes like a cube or the icosahedron that's been studied since antiquity. So from a linear point of view, we have polytopes and polyhedra. But the positive geometries here are interesting spaces, subsets of space that are defined by the positivity of certain functions. So this is at the most basic level. But I think in physics we're going deeper, right? We also want to integrate, and there are differential forms and things like that.
I think in physics it's even more basic. Just to bring it down to one simple sentence, I think my dream is that we can understand the physical observables that we like to calculate as some volumes, some positive volumes of some geometric structures. And so that idea I find extremely attractive, and I'm curious about how we can implement it.
One exciting feature about this is that these geometrical objects don't live in our ordinary space and time. So there are geometrical objects that are defined in the space of what we call particle kinematics, so the energies and orientations of particles that come into a scattering process. And then the probability for that scattering happens to be the volume of these geometrical objects. And different ways of dissecting that object, gives us our ordinary notion of evolution in space-time. And that's the sense how a space-time emerges, as a way of dissecting these geometrical objects that don't live in space-time.
That's correct. Of course, these can be in high-dimensional spaces that describe velocities, momenta. But I still think it's a good idea to keep our three-dimensional space for the intuition, right? So, for example, this glass is a positive geometry. It's given by the positivity of linear and quadratic equations. We want to measure how much water fits in here, and that's a volume. So I would say even calculations in three-dimensional space, we did one with the young people last night, can really help us guide our intuition. But ultimately, of course, we have to do this in a high-dimensional space.
Yeah, that's true. I'm surprised though, because I thought you would have given a different answer. I thought your answer was that positive stands for positive outlook on science in general, and on this project in particular.
I completely agree. Of course, we have I think we would probably not have been funded if this had been the negative geometry.
That's exactly right.
Yes. So yes, we are. I think we do all share a positive outlook and are enthusiastic about our science. I think that goes without saying.
Next question, I think, is for me, because it says the conference includes a special colloquium on positive geometry in cosmology, which is the colloquium I'm giving. So what goal are you, us, pursuing with regard to this special discipline? So I think one of the goals is to develop a new framework to describe the earliest instances in the history of our universe when the physical conditions were so extreme that they go beyond kind of our terrestrial experimental tests. And so we hope to develop a new mathematical language that can guide us what happened in those very first moments in the history of our universe.
And I'm very happy, Daniel, that you're giving this special physics colloquium tomorrow. It's also a way both for us to showcase a collaboration to the local physics community, and it's also at a very personal level. I mean, I got my math PhD in 1987, and I got to physics a year or two ago. And I think my colleagues, both here in Leipzig and elsewhere, do not yet know that I have any connection to physics. So at a very personal level, I'm very happy that you'll speak to the local physicists about cosmology.
I think cosmology is also a relatively large field, and so there's many different things one can understand by cosmology. So myself, I'm very curious to learn what's needed to be able to contribute more to this part of the project. And I think the specific areas of cosmology that are needed, it's hard to find them in textbooks. So because this is also new, so that's personal motivation for me to.
But
to learn
you
something
did
from
write
the
some
colloquium.
textbooks, no?
I did write the textbook, but a next textbook needs to be written in order to kind of fill this niche of.
So the next textbook will be part of an outcome of our project.
So there's one last one. Let me see. Okay, what are the special challenges faced by the 4 project partners, and how do you envisage them working together?
I think that's for our leader.
Yes, Johannes.
Yeah, what are the special challenges? I think there's a huge opportunity because we have all these talented people that can work together on this joint project. And so that's exactly in the spirit of the name of a grant. So it's a synergy grant. So we need to foster those synergies, and so that's up to us to make it happen. To make sure that the PhD students, postdocs, that all of the researchers in the collaboration have a chance to actually interact in a meaningful way, exchange, and such that the whole is more than the sum of the parts.
And yeah, there could naturally be some inertia now that we have this grant, that we could go back to our groups and our and to our communities. So I think the challenge is to kind of keep momentum up and really collaborate.
I think especially with this kickoff workshop, we're really off to a good start. I mean, as you mentioned earlier, the official start of the project is this summer, but I feel like it's already going. I mean, when I see all these people downstairs, the talks we had I think about 35 2-minute presentation of junior researchers that are eager to get going, that are already working on some aspects related to the key questions in our project. I think we have a lot of momentum, and it's up to us to keep that going.
So maybe that's the end of it. So I think we're very excited. We're very excited about this, and of course we invite the viewers of this to get in touch with us. I think there are many opportunities to stay positive.